We have now got to the point where, while we realise that investment analysis relies on precise forecasting, our discussion of cycles suggests that forecasting the future, where the future is the result of complex causality, human psychology, various unexpected changes in the community and the economy, this will make forecasting extremely difficult. And this is very close to the truth. However, the value of reasonably precise forecasts is so immense that considerable effort and resources have been turned towards trying to penetrate the future with precise forecasting methods. What we will now do is go through the various types of methods that have been used or are being used to forecast the financial future. We'll be looking at 4 generally. The first is multiple linear regression on time series. This is the most common method in use, and we will look at its advantages and shortcomings. Then we'll look briefly at harmonic analysis, which is a variant mathematical approach to forecasting cycles into the future. Thirdly, we will look at neural network analysis, and then finally we will review the value or otherwise of attitude and opinion surveys. Of all forecasting methods, multiple regression analysis tends to be the flagship. Certainly, it is the most commonly used mathematical approach. What comes second are attitude surveys, which we'll get onto later on. Multiple regression analysis makes the assumption that the variables that we are attempting to forecast are linear functions of a knowable number of causal factors. This means that if we want to forecast some variable, say property price, what we can do is express property price as a function of a set of causal factors, in this example referred to as x1, x2, x3, and so on, each with their own constant, in this case a1, a2, a3. And the factor, the dependent variable that we're looking to evaluate, is simply the sum of these linear influences on the factor itself. The equation is completed by adding a constant and also recognising in practice an error term. This approach has the advantage of reducing complex causality down to a pattern of linear relations. Linear relations, derived from the notion of a straight line, are mathematically simple in themselves, even though when they're added together, such as the above equation, they do start to look quite complicated. The advantage is that analysis of a complex linear relationship, such as the above equation, is fairly easy to do using standard statistical techniques, especially when one has the power of modern computers. For this reason, multiple regression analysis has become very, very popular because it suits the computational resources that are currently available. There are a couple of assumptions that need to be recognised when considering multiple regression analysis. The first is that the relationships between the various independent variables as causes are linear in their effect on the dependent variable. This means as the independent variables change, there is simply a linear effect on the dependent variable, and that's moderated by the value of the constant, which once evaluated does not change. Analysis is made up of using enough data to be able to evaluate the constants a1 to an and k. There are 2 further assumptions which are not at first obvious, but are vital to the effectiveness of the mathematical solution of multiple regression systems. And this is that the 2 conditions known as autocorrelation and multicollinearity cannot be present in the data. Autocorrelation is the condition where the dependent variable, such as the property price in this example, is a function of its own previous values. If the best predictor of price is previous price, we would say that the dependent variable price is autocorrelated. That is, it's correlated or derived from its own previous values. Multicollinearity refers to the condition where the various independent variables are in some way related to each other. For multiple regression analysis to work, the various independent variables, x1, x2, and so on, must be completely independent. There must be no correlation between them. The third major assumption with multiple regression analysis is that the relationships between the causes and the effects must be stable. This means that in addition to being linear, the relationships also must use the same constants through time. Multiple regression analysis can be applied to a number of different statistical analysis questions. For example, automated valuation relies on a form of multiple regression analysis where the various static attributes of a property are all reduced using the multiple regression technique. In forecasting, the independent variables tend to be today's values for various financial and social factors which are able to be evaluated. These factors are assumed to impact on the dependent variable that is being forecast, meaning that today's value of things like interest rates, GDP, wages, and so on have a constant, knowable, linear impact on property prices at some point in the future. This is expressed in the equation above. It is believed that if enough historical data that includes values of these various independent and dependent variables are amassed and analysed, good estimates of the various constants will be possible, and being stable, once they are evaluated in the historical context, they will then permit forecasting of the dependent variable into the future. We have mentioned that multiple regression forecasting is extremely common, but it's not without its downsides. The first is that while multiple regression analysis is certainly an easy form of analysis to perform given the resources that are available today, there is no convincing arguments regarding linear causality. That is, the assumption that there is a straight line relationship between interest rates and property prices has not been established. While we may be able to be confident that interest rates do have an impact on property price, the assumption that they're related through a simple constant has not become evident in the data. Likewise with the other variables that have been listed here. The example here, by the way, is only an example. The variables have been chosen as fairly typical and common variables that are associated with property price, but there are many others, and there's almost an innumerable number of multiple regression forecasting studies that have been done using various combinations of economic and social data. But the next downside that is extremely important is the investigation of the matter of autocorrelation and multicollinearity. Because what we find is that although multiple regression demands that there be no autocorrelation or multicollinearity, these are in fact common in practice. We talk of the naive forecasting of property prices based simply on the trend of where property prices have gone in the past. Generally, it can be said that if property prices have been rising for the last 6 months, a year, 5 years, then there's good reason to believe that they'll continue in that direction, at least for some modest period into the future. That is, the previous values and trends in property price are a very good indication of where property prices are going in the future. They are autocorrelated. Likewise, the assumption of no multicollinearity tends to be violated in the types of data which is commonly used as the independent variables for the multiple regression forecasting of property price. Interest rates are in fact related to wages, and likewise both are connected in complex ways to GDP. If we look at other economic, social factors that we might be using in multiple regression analysis to forecast property, we find that just about all of them exhibit all kinds of complex, interrelated correlations. That is, the data used in multiple regression analysis is penetrated with considerable amount of multicollinearity. While multiple regression analysis has been the most common form of mathematical forecasting used over the last 2 or 3 decades, the theory has not been supported in the data. Most embarrassing for multiple regression zealots is that naive models, that is, models assuming no more than property prices will continue in the way they've done in the past, often outperform them, are in fact statistically stronger. If a naive model can outperform the multiple regression model, there is really not very much reason to bother with its complexity. We find as well as that often the causality in the real world tends to be far more complex than simple linearity. We find that with things like interest rate and inflation, that we are told have a very simple relationship. If interest rates go up, it will cause inflation to go down, and the reverse. But in fact, there have been considerable periods in the past where both interest rates and inflation have moved together. Finally, multiple regression analysis tends to be confounded by the reality of cycles. Multiple regression analysis is not very good at predicting cycles, largely because it assumes this linearity. It's only when there are cycles in the data that the multiple regression model can come close to predicting a cycle in the dependent variable. But even then, the causality tends to be left in the dark. The failure of multiple regression analysis to deliver the answer to the question of forecasting has been a bitter pill for finance theorists to take, and many are still reluctant to accept it. However, many have moved on to other approaches, again borrowing from physics and mathematics, to use powerful mathematical tools to tame the data and be able to predict the future. One of these is known as harmonic analysis. Harmonic analysis borrows from the mathematics of physics and is based on the realization that any complex repeating pattern of behavior can be reduced to sets of sine waves. And by using the mathematics of sine waves, even the most complex pattern can be built up, so long as it does regularly recur. Harmonic analysis does rely on the assumption that property cycles, or the other cycles that it might be applied to forecast, are in fact regular. It assumes that the future will be a reproduction of the past. Ultimately, it can fit any pattern of historical data. However, the difficulty is that while harmonic analysis can certainly fit the data and come up with an impressive array of parameters that supposedly describe history, it doesn't necessarily project into the future, largely because it ignores totally the matter of causality. That is, harmonic analysis looks at the pattern of the past, but doesn't say where that pattern came from. And in particular, it really can't therefore say anything about where the pattern's going to go into the future. It ignores special unique features from the past and the future, what is referred to as shocks. And these shocks are often the elements that colour the data and change the direction of the future, sometimes irrevocably. From time to time, you will find forecasts using harmonic analysis, and in some cases they appear to have modest predictive ability. Whether or not they outperform multiple regression analysis is yet to be established. A completely different approach to understanding the patterns that exist in complex data is the use of neural networks. Neural networks are derived from psychology, where they use mathematical algorithms to parallel the behavior of the human brain. It really implies that in some ways markets behave like some sort of a social brain. While neural network theory has been rejected in psychology as a valid representation of the neural behavior of the brain, computer programs that are modeled on neural networks have continued to be used as curiously effective methods of being able to analyze and process patterns in complex data. The neural network looks at each data set and builds up a pattern of weighted causalities leading from the independent variables to the dependent variables. Ultimately, the causality in the model is opaque because of the complexity of the way that the neural network weighting operates. It's best to understand neural networks as capable of providing predictions, not explanations. That is, if it works, you cannot say why it works. It's simply satisfying to know that in some way it has applied an organized algorithm to complex data to come up with some sort of weighted probability on what's going to happen in the future. Curiously, neural network analysis does seem to provide practical results modestly superior to regression. To use neural network analysis, you need a computer program set up to perform it. After that, it's simply a matter of loading in your data, setting the neural network system to work, and it will basically learn the patterns and weightings that somehow are evident in the data, and then apply those when predicting the future. Neural network can be considered to be a highly stylized pattern fitting program operating on a computer. As such, it has the capacity to predict the future, in so much as the future is a reproduction of the past. Notionally, it seems to be possible for neural networks to be able to cope with fluctuations, although this is not necessarily a certain result. While it certainly appears to be effective as a pattern-fitting algorithm, it does depend on the amount of causality that's evidenced in the data. This means that the data must be able to capture all of the variety which is likely to be influencing the future, and therefore the scope of the data is the major limit for neural network analysis. The predictive superiority of neural network analysis is probably more of a criticism of regression than a positive statement about neural networks themselves, because what neural networks do is give you prediction at the expense of a credible understanding of cause. And ultimately, it's the understanding of cause which is the real source of scientific understanding. If we don't understand cause, we won't be able to understand what happens if new causes emerge or if the patterns of causality change. And this is certainly one of the blind spots of neural network analysis. That is, it's effective as a forecasting tool only so far as the future is going to be reflected as a perfect reproduction or extension of the past as shown in the data into the future. Any other impacts are likely to send the neural network well into error. This is especially problematic when we're looking at the possibility of chondriative cycles, where to capture the behavior of a chondriative cycle probably requires extremely good quality data reaching back at least a century. Considering the number of external changes such as technology and social changes that have happened over that period, the possibility of getting sufficient data to be able to capture that for a neural network analysis is pretty unlikely. This means that things like chondriative cycles, perhaps the GFC, would simply not appear as a result of a neural network analysis. With neural network analysis, we really leave the realm of precise statistical approaches or mathematical approaches to forecasting. We now move to attitude and opinion surveys. These consist of surveys of the opinions of experienced key industry people. For example, the API Market Sentiment Survey. It has been found that opinion surveys tend to evidence superior forecasting performance compared to all of the mathematical approaches that we've been discussing before. This tends to suggest the advantages of experience, and it somehow assumes that experienced opinion has a special merit. However, the way that experienced opinion turns into viable forecasts remains some sort of mysterious calculus, and opinion surveys give us absolutely no insights into the causality. When we conduct an opinion survey, we don't ask how, or at least we don't explore how an experienced practitioner comes to their conclusion, even though they might give some general influences that they consider influenced their decisions. Ultimately, the amount that these influences had an impact, and also the selection of what influences to select and which to reject, is left somewhat in the dark. Ultimately, opinion surveys, while they do give us what appears to be the best estimate of what the community, or at least the specialist community, believes is going to happen in the future, it doesn't tell us where opinion comes from. And like the neural network case, if we don't understand the causality, we have no way of knowing when that lack of causality is going to let us down. Closely related to the problem of attitude surveys or opinion surveys is the whole matter of whether a statistically analysed set of opinions does constitute knowledge. If I study the opinions of 20 or 50 or 100 people, what I can say is that I have knowledge of their opinions, but I don't have knowledge of what their opinions are about. At the end of the day, the average opinion of my 100 experts is no more than an opinion itself. It does not constitute knowledge. To illustrate that, let's consider a case study where we run an opinion survey of 100 deaf musicians about the merit of an opera that's played to them on a CD. Because they're deaf, they don't have any direct way of forming an informed understanding or knowledge about the quality of the music that's played to them. If it's played loud enough, they might be able to feel it vibrating their skin. Perhaps if they played it on a machine that has an array of flashing lights to show the music spectrum dancing across on an illuminated display, the deaf musicians might be able to get an idea of the rhythm. But that's about all. They only have an indirect and vague understanding of what it is they're being asked to comment on. In some ways, this is the same as what happens when we have experienced industry people passing comment on property. When our deaf musicians apply their memory of what good music felt like or looked like, they might be able to form a reasonable opinion as to whether the thing which is played to them is in fact good or not. But it will only be an opinion. It will lack the certainty of knowledge. And even though we have a large number of them, and maybe they're highly qualified musicians, at no point do we have a scientific causal connection between the music on the CD and their understanding of it in their minds. Likewise, when we go to ask opinions of industry specialists, while they may have considerable experience, they do not have a direct scientific understanding of the relationships between the causes and the effects, even though they might have indirect influences coloured by their past experiences. In both cases, we simply have opinions, and the statistical average of the opinions is itself only a representation of an opinion. It's not knowledge. When we look into history, we find that history is full of very powerfully and broadly held opinions that have, in the fullness of time, proven to be problematic. For instance, for about 1,000 years, it was believed that the stars were fixed onto a solid, invisible ball in the sky. Likewise, during the pre-modern era, leeches were considered to be able to cure disease by sucking out bad blood. Or, even recently, as living memory, salt was considered to be important in a healthy diet, although now it's important to keep it out of our diet. Likewise, there are many alive today who were brought up thinking that smoking was not harmful and in fact a vital part of a well-socialised behaviour. Lastly, we have the rather abhorrent evidence of Africans being considered as inferior humans. All of these were held by large numbers of educated people, but all of them have proven to be most objectionable and in some cases highly problematic. It all goes to show that even though opinions might be broadly held across a community and might be held by the most educated people in the community, they are simply no more than a belief which is based on something considerably less certain than truth. As well as that, opinion surveys have no explanatory content. They do not tell us why it was that the conclusions of the survey are connected or how they're connected to the supposed causes. A practical problem with opinion surveys is that they do not perform very well at forecasting changes in patterns. This is especially the case with their inability to predict sudden changes when property markets do go through periods of correction, say the crash following a boom. And while this only happens infrequently, it tends to be the most important forecast that a property person needs to be aware of. Lastly, if opinions are better than the best mathematical methods, then we are not actually dealing with science. We're dealing with some other form of understanding or belief, perhaps even some kind of quasi-religious faith in the experience of those whose opinions we seek. It's certainly not something based in conventional science. We therefore come to the end of our survey of forecast methods with the conclusion that there really are very few ways of forecasting the future that really should command our respect as scientifically robust. The best we can find is the opinion surveys that in some mysterious way give us the answer to where the future is going, or perhaps neural networks that likewise are able to capture the complexity of human systems and predict the future only so long as it is actually hidden in the evidence of the past. From this, however, we then move into the more practical question of the problem of financial forecasting, because we find in here there's an extra set of issues that we need to come to grips with. First of all, we need to be aware that financial gain relies on imperfect markets. This is important because imperfect markets are the very thing that our economic system is supposed to eliminate. Economic theory is supposed to produce perfect market competition, and in fact, all of the benefits of our free market approach, whether it be the privatisation of infrastructure or the deregulation of our foreign trade, is all based on a belief in the existence of perfect markets. And yet, finance relies on imperfect markets, on the fact that there are advantages that other people do not know about, which is almost a definition of market imperfection. If everyone could know the future, effectively there would be no opportunities for financial gain. This is because we have seen in the past that financial gain comes from being able to recognise mispricing in the market. If the market undervalues something, say a piece of real estate, and we understand its true value, if we buy that real estate, we should be able to buy it for a lower price because the market generally undervalues it, and we will benefit. If the market had a correct understanding of that property's value, its value would be higher, and when we bought it, there would be no net advantage to us. This means that any widespread knowledge on finance or property will tend to lose its value, at least its value in terms of returning a special profit to us as an investor. For these reasons, we can conclude that while we do notice that there are financial opportunities and property opportunities, these stand out as proof that economic theory is in fact not an accurate model of the real world. This should come as no surprise, because it's been understood by many people for some time. However, economists and politicians don't seem to have learnt it yet. But the practical problem for us is that given that market imperfection is the reality, we find it difficult to get that information and those techniques that would give us the benefit of accurate insight, as opposed to the market in general that does not have that. The very fact that you are currently students learning financial investment analysis means that there are things that we will be teaching you that if the community in general were aware of, it would colour the pricing of real estate and therefore reduce the opportunities for profit, which no doubt is why many of you have joined the course. Any widespread knowledge loses its value in the area of finance. There is a separate problem that comes from the matter of financial forecasting, and that is that the data comes from a closed set where today's values come from yesterday's values. Or putting in the context of forecasting, the forecast of tomorrow is based on an understanding of the values of the same closed set of parameters today. This means that financial environments operate within a closed environment where there is rife multicollinearity and autocorrelation. And you'll remember that these are exactly the elements that prohibit the precise use of multiple regression analysis. If we look at similar instances in nature, we find that they are also the hardest ones to forecast. There are some natural systems that can be explained by simple mathematical relations and evidence the circumstance of having their values determined by the previous values of a similar closed set. However, the maths does not lead to predictability. The best example of this is the weather, where elements such as temperature, air pressure, wind direction and velocity can all be understood in terms of the circumstances of other weather parameters in the past. However, the weather has shown to be particularly difficult to predict with any kind of accuracy. It was the attempts by scientists to understand and predict the weather that led to a new and exciting branch of mathematics known as chaos mathematics. Chaos mathematics describes the behaviour of fluctuations in the natural world. While these certainly are best represented by the weather, they also include many other things, such as the shapes of clouds, the turbulence of gases flowing past a stationary object, and laminar flow, and even the behaviour of dripping taps. There are many regular or pseudo-regular phenomena in nature which seem to be nicely described by chaos mathematics. The characteristics of chaos mathematics is that they're defined by simple sets of mathematical relations or mathematical equations. However, even though the mathematical relations between the various parts of the system are well known and known with certainty, the system itself cannot be used to determine the future. That is, they're non-determinate. Technically, for the mathematically minded, we say that chaos mathematics relies on systems of non-differential equations. These are found to be more common, both conceptually in mathematics and physically in the physical world. What we find is that while clouds and turbulence and so on are examples of chaos, Well-behaved phenomena, such as the pleasant sound coming from an organ pipe, which gives us a nice regular sine wave, tend to be special cases. The more common case is the random fluctuation, which, say, is represented by the prediction of the weather, by the prediction of, say, the temperature tomorrow, or whatever. If you look at the shape of clouds, for example, you find that while clouds are a overall generally predictable shape, the actual surface of them is almost endlessly interesting. No two clouds are the same. And yet, the mathematics determining where the cloud forms and how it forms is actually quite simple. The curious thing about chaos mathematics is that you have simple mathematical equations that can produce extraordinarily rich and varied physical and social phenomena. To identify when a physical or social phenomena is going to be following chaotic patterns rather than something more predictable, we can look to several indicators that suggest the existence of chaos in the behaviour. The first sign which is likely to indicate that a chaotic system could be present is that the dependent variables are a function of their own previous values, or in systems where you have a closed system, such as the weather, where the value today is a function of values taken from the system from previous periods. That is, you have systems that display autocorrelation and multicollinearity. Another indication of a chaotic system is that while they sometimes behave as regular cycles, more often they behave as pseudo-random cycles, where the fluctuations tend to fluctuate about what is known as strange attractors. In the case of property cycles, while we might talk about a 8 to 10 year cycle, what we're really saying is that the period of the fluctuation is somehow attracted around the centre point of 8 or 9 years, and any particular cycle can range either side of that. Likewise, the amplitude of the fluctuations, again, tends to be neither too high or too low. We see this in the weather, where on any particular day we might be able to say what we expect the temperature to be, but we know that that's only a reference point, some sort of a strange average where the actual temperature is going to vary either side of that expectation somewhat. What this means is that what we think of as property cycles are in fact almost regular fluctuations, where the amplitude, in other words the severity of the cycle, varies, and also its frequency, that is, the number of times it occurs in a particular period. With both varied amplitude and frequency, while we have something which vaguely is cyclical, it's really more correctly only a fluctuation. We can look at the weather as a chaotic system because it has these characteristics. The weather parameters operate within general limits. On any particular day of the year, we know that the temperature is not going to be beyond certain upper and lower limits. Likewise, each parameter is a function of the previous weather conditions. The temperature today is a function of yesterday's weather, somewhere in the world at least. Thirdly, there are simple equations which define each parameter, and so today's temperature is a relatively simple equation based on yesterday's temperature, pressure, wind direction, and so on. Fourthly, we find the weather, although generally within certain bounds, gives us almost endless variety. And lastly, while we can understand the weather in terms of the individual equations that define each parameter, we can't predict it precisely. Let's now look at a simple example of a chaotic system. In this case, we're looking at a very simple equation which has the capacity to behave in a chaotic way. The equation we're looking at is a parameter y, which we're trying to evaluate for time t, which is equal to a constant times the previous value of y, that is yt minus 1, minus the same constant times yesterday's value, or the previous period value of the parameter y squared. This equation has been graphed for two different values of the coefficient a, as shown in the graphs in the centre of the slide. We will see on the left-hand example that when a has a value of 3.85, the value of yt tends to vary pretty much as a constant regular cycle. This gives quite an impressive and apparently predictable result. However, if we change the value of the variable a merely to 3.80, we find that the shape of the graph produced is quite different. Here we see that while there appears to be regularity to the eye, a close inspection reveals that the regularity is more of an illusion than a fact. The distance between successive peaks and troughs in the graph changes, and also the amplitude between the high point falling to the low point and back again is different for almost each one of the traces. That is, that the trace on the right-hand side is only fluctuating with a certain variation in wavelength, period, distance between successive troughs or peaks, and also a certain amount of variety in the amplitude or the height between a peak and a trough. What we can conclude from this example is that minor changes to the parameters can totally change the behaviour. If nothing else, it means that if we can understand our chaotic relationship in terms of its mathematical equation, that might be only one part of the problem. The second part of the problem of prediction is to be able to know the value of the coefficients with extreme precision. In the example we're looking at here, we're talking about an error or a change in the parameter a of only about 1.5%, and yet it makes considerable difference to the overall pattern and predictability of the result. There are many practical and theoretical reasons to conclude that financial systems, and especially those connected with the property markets, do exhibit all of the characteristics of a chaotic system. However, chaos mathematics, while it gives a certain level of satisfaction in providing an understanding of the behaviour of many social and physical phenomena, is not without its downsides. In practice, in order to use chaotic systems to forecast the future, we need extremely large amounts of data. This is simply impractical at this present time for property purposes, especially since property tends to relate to individual properties. The second downside is that while chaos mathematics can conceptually explain the causality that is behind behaviour, it's not so good at predicting the future. It goes even worse than that. The one thing we can certainly conclude when we have identified the existence of a chaotic system is that we cannot predict the future because of the very behaviour of chaos maths. If property is an example of a chaotic system, it certainly explains why regression does not work. And we keep coming back to those little demons, the autoregression and multicollinearity, which were not supposed to be present in our autoregressive system, but are known to exist in practice for the property markets. And this is exactly the material which is needed in order to have a chaotic system. And so what we have in recognising chaos in property systems is an explanation for why regression doesn't work. We can now move to make certain conclusions about the matter of forecasting. First of all, we can recognise that finance is a wager on the future. It's a bet that the future will not be like other people think. And that is the opportunity for financial gain. In order to have a better understanding of the future than the rest of the community, many people turn to mathematical models. But we find that the most effective of these tend to lack causal integrity. And by this is meant that while they may have certain historical success in fitting patterns, their insights into what is actually the cause of why the different variables move is not very satisfactory. What this means is that the mathematical methods are practically useful only when they're not needed, and in particular they all tend to fail when they are most needed, and that is in predicting the sudden changes that characterise economic corrections, especially those at the peak of a booming market. Thirdly, we have found that opinion methods are simply opinions. They also fail when they are most needed, even though for much of the rest of the time they do create the illusion of some sort of special knowledge. While opinions do have merits, and having a belief based on an opinion is certainly better than having no belief at all, it's very important that we're aware of when our beliefs are based on opinions and not some sort of scientifically or philosophically defensible position. The greatest problem with opinion methods is that they also fall foul of the problem of failing when they're most needed. What we have seen is that the most likely causality is known to give us a chaotic system. And the one thing we can conclude from chaotic systems is that they do not yield to prediction. It's important for us to explore chaos better, and I do recommend that better students explore chaos mathematics and the implications of chaos for finance further. Ultimately, while we may continue to attempt to use forecasts into the future, we have to be aware that at this point in time at least, there are no generally known robust methods of precisely forecasting the future. The only major opportunity that we can conclude from our exploration of forecast methods is that since our profit is dependent on inferior forecasts from our opposition or the market in general, so long as your opposition adopts a method that is inferior to yours, you are likely to end up in front. All this is not meant to discourage you from the matter of forecasting, because after all, you will all be using some sense of forecasting in just about all of your professional lives. But it's very important for you to go in with your eyes open and realise that those people who do take forecasting too seriously are likely to be the ones that will endure the greatest costs when they give it too much value. It also is important for you to be on the lookout for places where our commonly held beliefs about the way that society and the economy behave are not in fact well conformed to reality, and that is, the causal theories are not in fact true. This is certainly the case with much economic theory, but there are other aspects as well. The opportunity is to understand the world in a way superior to those around you, and this will lead to success.